Our lesson today is on zeros and factors of polynomials. We're going to learn how to find all the zeros of a polynomial. Zeros for a polynomial can be both real numbers, in which case they'll be x-intercepts, and they can be non-real complex, which just means they are imaginary. And so they don't intersect the x-axis, but they're still solutions to our polynomial equation. And then we're, of course, going to find polynomials with specified coefficients and zeros. We're going to factor our polynomials into linear and irreducible quadratic factors with real coefficients. So the coefficients will be real numbers. And then we'll also factor them completely into linear factors. So linear factors are first-degree factors. And if we factor completely into first-degree factors, we will have complex coefficients, which means our coefficients may be real numbers, or they could be non-real complex or imaginary numbers. Okay, so our first page here is just a number of theorems that we need to go through just to have sort of a solid foundation or a background to understand some of the attributes of polynomial functions, and then we can use that going forward as we do our work with polynomials. So first one we have here is the fundamental theorem of algebra. Now the fundamental theorem of algebra tells me that every polynomial, so any polynomial you can come up with that has a degree greater than 0 has at least one complex root. Okay, so I will have any polynomial, as long as the degree is greater than 0, so 1, 2, 3, has at least one complex root that I can solve for. Now remember, every real number and every imaginary number are elements of the complex number system. So as a review, we've talked about this previously, we've got the complex number system. And within that complex number system, we have two branches. One is the real numbers. And the symbol we use for that is the R with the double egg. Okay, in this case, B is equal to 0. Okay, these complex numbers are in the form A plus BI. So B would be equal to 0, and I just have the real element. And then the other is imaginary numbers, or they're sometimes referenced as non-real complex, which just seems like an awful lot of words when you can say imaginary. So in that case, in our imaginary element, then B is not equal to 0. I have some element here for B, okay, for that imaginary part. So real numbers and imaginary numbers both fall under the umbrella of complex numbers. Now remember, with our complex numbers, A is the real portion, and then the BI, that is our imaginary component. Okay, so for example, 6 plus 4i is an imaginary number because it has the imaginary component. 7 is a real number. 4i is an imaginary number, okay? Each one of these is a complex number. They are all complex numbers, okay? The first one is imaginary because it has that imaginary component. 7 is real. If I wanted to write this as a complex number, you could write it as 7 plus 0i. And then 4i is also imaginary, and you could write the real component as 0 plus 4i, which we don't typically do. We write them in the simplified version, which would be 6 plus 4i, 7, and then 4i. Okay. The complete factorization theorem tells me that every polynomial of degree greater than or equal to 1 can be factored into a product of n linear factors. So whatever the degree is tells me what the number of linear factors is. And then the caveat here is this: I have to be able to use complex coefficients. So complex coefficients means I have to be able to use imaginary numbers if I'm going to factor it into a product of linear factors. So everything is first degree. Okay, so linear factors are just factors in the first degree. So those are the ones that are of the format x minus c, and that's understood to be first degree. So the polynomial would be written then as p of x equals a is my leading coefficient, times x minus c1 times x minus c2, x minus c3, x minus c4, all the way down. And each of these c values, these are the roots or the zeros of the polynomial. Okay, the zeros theorem tells me that every polynomial, again with degree greater than or equal to 1, has exactly n zeros, provided that a zero of multiplicity k is counted k times. Okay, so the polynomial degree tells me how many zeros there are, and it just depends on how I write them. So for example, if I gave you the polynomial below, 2x to the 6th minus 8x to the 5th minus 62x to the 4th plus 464x cubed minus 1098x squared plus 1080x minus 378. This is a 6th degree polynomial. Well, the zeros theorem tells me that there are 6 zeros, okay? But there's a caveat here. I have to count the multiplicities. So I can see that my zeros, based on my factors, are at 3, 1, and -7. So that's only 3 zeros, okay? And the theorem tells me I have 6 zeros. Well, I could rewrite this as 2 times x minus 3 cubed is the same as x minus 3 times x minus 3 times x minus 3. X minus 1 squared would be x minus 1 times x minus 1 times x plus 7. So as long as I'm allowed to count each one of these individually, I have 1, 2, 3, 4, 5, 6 separate linear factors. Each one of these is degree 1. Okay. And so my degree is 6, and I have 6 different linear factors. So again, I can look at the multiplicities and do this without writing all of this out. I know the multiplicity at the 0 for 3 was 3. The multiplicity when the 0 was x equals 1 was 2. And then the multiplicity of x plus 7 was 1. If I add this up, I get 6. And that equals the degree of the polynomial. Okay, the linear and quadratics factors theorem tells me that every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors, also with real coefficients, okay, which means no imaginary numbers. Now, note, an irreducible quadratic, because I've been told I can factor this into a product of linear, so that's first degree, and an irreducible quadratic, so a quadratic, of course, is second degree. Okay. Well, an irreducible quadratic has no real zeros and can't be factored without using non-real complex numbers, or it can't be factored without using imaginary numbers, without i's. So that's the reason. If it could be factored using real numbers, then we would have continued to factor it and come up with linear factors. So for example, f of x equals x squared plus x plus 4, I'm told has no real solutions and is an irreducible quadratic. So an irreducible quadratic means you can't factor it without using i's. So without using imaginary numbers, it can't be factored. Okay, and so in fact, if I asked you to factor this, okay, we would have to use the quadratic equation because it doesn't factor nicely. Or if I would do x equals -1 plus or minus the square root of 1 squared minus 4 times 1 times 4, all divided by 2 times 1. So x equals -1 plus or minus the square root. 1 squared is 1 minus 16, so -15 divided by 2. Now, because I have a negative number under the radical, I know that I'm going to have to use I, or the imaginary unit, to factor this or to solve this. So x equals -1 plus or minus the square root of 15 times I divided by 2. If I want to split that, that means x equals -1/2 plus or minus the square root of 15 over 2 times I, and x equals -1/2 minus the square root of 15 over 2 times I. Be really careful that the I is not under the radical. A lot of times I'll put like a little hook here just to make it really evident the I is not under the radical, okay? Now, these are non-real complex numbers. Okay, I should say actually they're non-real. Let's be more specific here. Non-real complex roots. Okay, so they are solutions or they are roots, but they are not x-intercepts. In order to be an x-intercept, you have to be a real number. Okay, and so these are my answers. So normally if it was an x-intercept, if it was a real number, you would write the value comma 0 to indicate it's a point and it crosses the x-axis. But for these, you just write the x values. And so I can see these are in the form of a plus bi, where a for each of them is -1/2, b is the square root of 15 over 2, or negative the square root of 15 over 2. And just to be really specific here, this first one I should have written is just positive. So please make sure you make that adjustment in your notes. Okay. Okay. So that's all of our theorems. We've talked previously about zeros and factors of polynomials in the factor theorem. The factors theorem tells us this: if x equals a is a zero of the polynomial, then that means that x minus a is a factor of the polynomial, okay? And so I've given you an example here. I've said given f of x equals 18x cubed plus 75x squared plus 63x minus 30, and I want you to determine is -1 or -2 a real zero of the polynomial. Now, we can do this using synthetic division is probably the easiest way. So let's assume we want to find out if -1 is. If -1 is a 0, then my remainder should be 0. Remember, I'll use the leading coefficients, 18, 75, 63, and -30. The 18 comes down. This is 18 times -1 is -18. That's 57. -57 plus 63 is 6. And then -6, so -36 is my remainder. So because the remainder is not 0, then that means that x equals -1 is not a 0 of the polynomial. Because I'll have the point -1, -36 on this graph. All right, so let's try the other one, -2, again using synthetic division. 18 times -2 is -36, plus 75 is 39. 39 times -2 is -78, plus 63 is -15, times -2 is +30, and so the remainder, let's not write it there, is 0. So since the remainder is 0, then I know I have the point -2, 0 on the graph, and so therefore, those 3 little dots mean therefore, x equals -2 is a 0 of this polynomial, which is very useful because my goal in all of this is to take these large polynomial functions, something to the 17th degree or the 34th degree, and be able to factor them. And I know I can factor them completely based on my theorems on page 1. I can factor each one of them all the way down into a product of linear factors as long as I'm allowed to use complex numbers. If I'm not allowed to use complex, non-real complex numbers, then I can factor them all the way down into linear factors and irreducible quadratics. So I could take something like a 17th degree polynomial and I could factor it, and I know I'll have 17 different factors, okay, as long as I can count the multiplicities. So I may not have 17 distinct roots, but if I can count each one of the factors based on their multiplicity, I'll have 17 separate factors. And so that's where we're going with this. Okay, part B says use the result from part A and factor the polynomial completely. This is where it's going to be really important, into the product of linear factors. So everything is first degree with real coefficients. So no imaginary numbers are going to be allowed here. Okay, so since I know that x minus 2 or x equals -2 is a 0, then what that means is that x plus 2 is a factor. Okay, so this polynomial f of x can be written as x plus 2 times the quotient. Remember, the quotient is here. So the quotient is 18x squared plus 39x minus 15. Now I need to factor this into a product of linear factors. So everything has to be first degree. Right now, x plus 2 is to the first degree, but 18x squared is second degree. So I need to continue on. So to make the numbers a little easier to work with, from 18x squared plus 39x minus 15, I'm going to factor out a 3. So 3 times x plus 2. 18x squared divided by 3 will leave me with 6x squared. 39x divided by 3 is 13x. Minus 15 divided by 3 is minus 5. Just makes my numbers a little easier to work with. And then I can either use the quadratic equation or I can split the middle. I'm going to split the middle with this one. So I need two numbers. When I multiply them, I get a times c. So a times c is 6 times negative 5, which is negative 30. And I add them to get b. b is 13. So two numbers, when they're multiplied together, give me negative 30. When they're added together, they give me positive 13. So that would be negative 2 and positive 15. And those are the values I'll use to split the middle. So f of x equals 3 times x plus 2 times, I'm splitting the middle, so I'm taking this term here in the middle, 13x. I'll just carry the 6x squared down. 13x, this will be negative 2x plus 15x. And you can see negative 2x plus 15x, if I add those together, I come back to 13x. I'm right back where I started. So I haven't changed anything. I've just split the middle. And then I'm going to factor by grouping. So f of x equals 3 times x plus 2. This was drug along. From the first two terms, I factor out a 2x. Leaves me with 3x minus 1. From the second two terms, I'll factor out a 5 and 3x minus 1. It should all be in parentheses. F of x equals 3 times x plus 2 times, these both have a common factor of 3x minus 1, so that can be factored out, times 2x plus 5. Now, everything has been factored into a product of linear factors with real coefficients. Everything here is first degree, first degree, first degree, first degree. All of my coefficients are real numbers, meaning I don't have any imaginary numbers. There's no i's. So at this point, I know I'm done. Now, a quick little aside here that I want to talk through for just a second. I'm actually going to scroll all the way to the bottom, so I've got some room to work. Okay. If for that problem, let me rewrite it here. It was f of x equals, we had it down to x plus 2, or actually let's do 3 times x plus 2 times 6x squared plus 13x minus 5. Let's assume you didn't want to split the middle, but what you decided to do instead was to factor the 6x squared plus 13x minus 5. You're going to use the quadratic equation. So x equals negative 13 plus or minus the square root of 13 squared minus 4 times 6 times negative 5, all divided by 2 times 6. All right, 13 squared is 169 minus 24 times negative 5. So that is the square root of 289 all over 12. So x equals negative 13 plus or minus, the square root of 289 is 17 over 12. I split this, so x equals negative 13 plus 17 over 12. 4 over 12 would be 1/3. And x equals negative 13 minus 17 over 12. This is negative 30 over 12, which is negative 5/2. Okay? And so my factors then, based on this, would be x minus 1/3 and x plus 5/2. But if you scroll back up to the top, that is not what we had. That is not what we found. Okay, we found the factors to be 3x minus 1 and 2x plus 5. Now, something we need to look at here. Our original polynomial, way up at the top, go way up here. Our original polynomial was 8x cubed plus 75x squared plus 63x minus 30. When that's factored, okay, those are integer coefficients. There's no fractions there, okay? So when that's factored, I can't have any fractions. So all the way back down at the bottom here, if I continued on this path and I said, let's assume we continue to factor this and we said f of x equals, and I'm just going to bring these down, 3 times x plus 2, and then times my factors, x minus 1/3 and x plus 5/2. Okay, you can see if I checked my work and I multiplied everything out here again, so let's assume I just multiplied the first terms. So 3 times x times x times x, that would be 3x cubed. And then I would do the rest of it as well. Well, look at the first term in the original polynomial. I should come back to the original polynomial. Well, the first term is 18x cubed. Okay, that doesn't agree. And the reason it doesn't agree, is because I've got these fractions. Okay, well, to fix this, what you would have to do then is x minus 1/3. We know that's a 0, so that would be equal to 0. So x equals 1/3. If I multiplied both sides by 3, I would get 3x equals 1, and then to find the factor, 3x minus 1 equals 0. And that's what I would want to use. For the other one, x plus 5/2, so x equals negative 5/2, multiply both sides by 2, 2x equals negative 5, and so the factor would be 2x plus 5 equals 0. That would take you back, and that gives you your factored form. So just realize after you find your factors, multiply together your first terms in each factor and make sure that you come back to the first term in that original polynomial. If you have integer coefficients in your original polynomial, you can't have fractions in your factors because otherwise you won't come back, and so you'll have to make this adjustment. So I just wanted to point that out to you. Okay, back up to our notes where we were. Where are we? Okay, so we found our factored form of our polynomial. F of x equals 3 times x plus 2 times 3x minus 1 times 2x plus 5. And again, if I multiplied all these together, I would have 3 times x times 3x. So that's 3x times 3x is 9x squared times 2x. That would be 18x cubed. And that's the first term in my original polynomial. Okay, so and then part C, what are the real roots of f? So my real roots are x equals negative 2, x equals 1/3, and x equals negative 5/2. All I've done is I've taken my factors, set them equal to 0, and solved. So 3x minus 1 equals 0. Okay, which these are the same values I got from the quadratic equation. Okay, so those are your real roots. And because these are real numbers, they are my x-intercepts. They're the x values in my x-intercepts. So if I asked you for the x-intercepts, you would tell me negative 2, 0, 1/3, 0, and negative 5/2, 0. Those are always written as points. Okay, so let's talk about the irreducible quadratics. So a quadratic polynomial that has real coefficients and no real zeros. So what that means is when you try to factor it, you get imaginary numbers. What you end up with is when in the discriminant is negative, so under the square root, you end up with a negative number, okay? So if that's the case, that's what we call an irreducible quadratic. Okay, And again, what that tells us is that the discriminant, the value under the square root, is less than 0, and that would produce square root of a negative number, which means when you solve that, then your zeros, you're going to still have zeros, but they're just not x-intercepts. Your zeros are what we call non-real complex numbers. Okay, for our next example, we're given the polynomial p of x equals x cubed plus 4x squared plus 7x. And we're told to factor this polynomial p of x into a product of linear and irreducible quadratic factors with real coefficients. So linear, first degree, irreducible quadratics, so that means second degree, because it's irreducible, everything will have a real coefficient. So no imaginary numbers, no i's, okay? So you're gonna have to really read carefully on these, because each one of these problems, you're either gonna factor it into a product of linear and irreducible quadratics with real coefficients, or in part B, we're gonna factor it into a product of linear factors, so nothing higher than degree 1. But if I ask you for that, I have to allow you to use complex coefficients, which means you have to have the ability to use i's. It doesn't mean you will, but you have to be allowed to. Okay, so back to part A. Factored into a product of linear and irreducible quadratic factors. So p of x, I can see that each term has an x in it, so I'm going to factor an x out. That'll leave me with x squared plus 4x plus 7. Now, the way to determine, I can see this as a quadratic because it's second degree. The way to determine if it is irreducible is to look at the discriminant. So I'm going to look at the discriminant b squared minus 4ac. If that's negative, if it's less than 0, then that means that this is irreducible. So I don't even have to use the entire quadratic equation. So b squared will be 4 squared minus 4 times a, which is 1, times c is 7. So that's 16 minus 28. So this is negative 12. So that means I would be taking the square root of negative 12. Well, that, of course, is going to produce an imaginary result, okay? So I know this is an irreducible quadratic. So at this point, I'm done with this problem. So as a product of linear, here's my linear, and irreducible quadratic, here's my irreducible quadratic. I'm done. Okay. For part B, factored into a product of linear factors with complex coefficients. So again, if it asks for complex coefficients, that means I have to be allowed to use imaginary numbers. So p of x equals x times x squared plus 4x plus 7. And this, of course, is second degree. I need this to be linear factors. Well, to find the factors, I'm going to use the quadratic equation. So x equals negative b, negative 4, plus or minus the square root. B squared is 4 squared minus 4 times 1 times 7. This is the same thing I actually just did above here. I'm just rewriting it out. Times 2 times 1. X equals negative 4 plus or minus the square root. This is 16 minus 28, which is negative 12, divided by 2. So I need to simplify. When you reduce, I always ask you guys to reduce the first terms and then the second. You do better that way. So this is negative 2 plus or minus. Now the square root of negative 12, bring the I out front. So it's 2I times the square root of 3 all over 2. Don't lose the 2 along the way. So x equals negative 2 plus or minus I times the square root of 3. Okay, so that means x equals negative 2 plus the square root of 3i. I'm going to write it this way so you can see what the a and b values are. X equals negative 2 minus the square root of 3i. These are non-real complex roots. Okay, so this is what I'm going to use for my factors. So p of x equals x times, my first factor is x minus, my first result, negative 2 plus the square root of 3 times I. My second factor, x minus, because remember, whatever your root is, your factor is x minus that value. Negative 2 equal, nope, not plus minus this time, square root of 3i. And at that point, I'm done. Now, if you want to clean this up a little bit and distribute these negative signs through, you can. You don't have to, but you can. So this is x times x plus 2 minus the square root of 3i, x plus 2 plus the square root of 3i. And so I would accept either one of these answers. Okay, so that's it. So that is factored into a product of linear factors. Everything is first degree. This is first degree, first degree, first degree. But I had to allow you to use complex coefficients, which means I had to allow you to use i's. Okay, and in fact, we needed i's to be able to factor this into linear factors. Next, we're going to factor p of x equals x squared plus 36 into a product of linear factors with complex coefficients. Now, there's a couple different approaches you can take to this one, and I'll show you both ways. One is you could use the quadratic equation because this doesn't factor, okay? If you thought it factored to x minus 6 times x plus 6, you were wrong because positive 6 times negative 6 equals negative 36, not positive 36. So you can use the quadratic equation. So x equals negative b. B here is 0, right? If I rewrote this in standard form, it'd be x squared plus 0x plus 36. So b is 0. So 0 plus or minus the square root of 0 squared minus 4 times 1 times 36 all over 2 times 1. So x equals plus or minus the square root of negative 144 divided by 2. So that means x is equal to plus or minus 12i divided by 2, which is plus or minus 6i. Okay, so that's one way to do it. So if I was factoring this, I'd have p of x equals x minus 6i and x minus negative 6i. You can leave it like that if you want, or you can simplify to x minus 6i times x plus 6i. Okay, so it's fully factored there. I'm just going to show you the other approach that you could take is we know that the zeros occur where this is set equal to 0. So x squared plus 36 equals 0. And you're going to solve for x. And so x squared is equal to negative 36. Take the square root of both sides. X equals, remember this is plus or minus 6i. Okay, so a few less steps there. Some of you at this point are more comfortable with the quadratic equation. You can take either approach. It doesn't make any difference. You get the same answer. Okay, for the next one, we're told we're going to factor q completely into a product of linear factors. That's important, so circle it. Linear factors, so everything's going to be first degree with complex coefficients. So that means i's are okay. If you end up needing to use imaginary numbers, you can. If it were to say real coefficients, you couldn't use imaginary numbers. All right, so q of x equals x cubed minus 3x squared plus 3x minus 2. Now, that's all they give me, and I'm supposed to factor this. I've got nothing to work with, like absolutely nothing. If I tried to factor by grouping, let's see what happens. I could pull out an x squared. That would leave me with x minus 3 plus, well, there's nothing I can do here, 3x minus 2. These don't match, okay? So that means you can't use factor by grouping, so that's not going to do me any good. So I'm going to have to use this graph that they've given me over to the side. No matter of fact, they even said, given the graph. So let me erase this other stuff because I'm going to need this space to work. Okay, so if you look at the graph, I can see I have a point here at 2, 0. Okay, so what that means is that x equals 2 is a root, and that means that x minus 2 is a factor, and that is going to be super convenient. So x minus 2 is a factor. So q of x will equal x minus 2 times something, times whatever the quotient is, okay? Well, in order to find the quotient, I'm going to use synthetic division. In fact, I'm going to come down here. We're going to divide by that root of 2. Using the leading coefficients from the original polynomial, I'll have 1, -3, 3, and -2. So this is 2, -1, this would be -2, 1, 2. Shockingly, the remainder is 0. I knew it would be 0, right? Because the point is 2, 0 on the graph. And so that's what told me that x equals 2 was a root and x minus 2 was a factor. But now what I'm looking for here is the quotient, and I've got it. Quotient is here. So I can use that. So I'll have x minus 2, let me use parentheses here, times x squared minus x plus 1, that quotient. Okay, now I'm still not fully factored because remember I have to get to a product of linear factors. So everything has to be first degree, and right now I've got a quadratic. So I'm going to see if I can finish factoring this. So q of x equals x minus 2. Can I factor x squared minus x plus 1? No, it doesn't factor easily. So what I'm going to have to do is I'm going to have to use the quadratic equation. So let me do that here. So x equals negative b, so negative of -1, plus or minus the square root of b squared minus 4ac all over 2a. X equals 1 plus or minus -1 squared is -1 times -1, which is +1 minus 4. This is the square root of -3 over 2. So x equals 1 plus or minus the square root of 3i all over 2. Okay, so if I want to write these separately, which I think is better, x equals 1/2 plus the square root of 3 over 2 times I, and x equals 1/2 minus the square root of 3 over 2 times I. There's my roots. Okay, they're not real numbers, so they're not x-intercepts, and I can see the only x-intercept I have is at 2, 0. But these are solutions to this problem, and it gives me my other factors that I need. So I've got q of x equals x minus 2 times x minus 1/2 plus the square root of 3 over 2 times I, and x minus 1/2 minus the square root of 3 over 2 times I. Okay, again, you can leave it like that. If you want to distribute the negative sign through, you certainly can do that as well. But that's your factored form. Everything is linear. It's all first degree. This is first degree, first degree, first degree. But I had to be allowed to use complex coefficients, which means I had to be able to allowed to use i's, imaginary numbers, when I found my factors. And in fact, I needed to. I used i's when I did. Okay, so that's that one. All right, now, if we were in class together, I would have you do the next one on your own. And I would have you then come back and check your work. So I'm going to have you do that now. I'm going to have you pause the video in just 1 second. Before you go, notice, I'm giving you a little hint here, the real 0 has a multiplicity greater than 1. So think through, what does that mean? What are you going to do with that? And how can you use that information as you factor this 5th degree, it's our biggest one yet, 5th degree polynomial. Okay, when you factor this, you know because it's a 5th degree polynomial, you're going to have 5 linear factors. Okay, so take a shot at that and come back and check your work. Okay, so hopefully you're back and you can check your work. Now, I can see that the multiplicity, because of the way this crosses the x-axis here, is 3. And so that means my factor is x minus 1 cubed, and my root, or my 0, is x equals 1. Okay, so I can use that and synthetic division to solve down and find my quotient and find the factor. So I use synthetic division with x equals 1 here. And then that gives me this quotient. And then because it's x minus 1 cubed, so 3 times x minus 1 times x minus 1 times x minus 1, I do it again and I get a new quotient. And then I do it again a 3rd time and get a new quotient. And so that gives me 3 factors of x minus 1 times x minus 1 times x minus 1 times the quotient of x squared plus 9. Now I was told I had to factor this into a product of linear factors with complex coefficients, so I can't have anything of degree 2. Everything has to be first degree. So I take the x squared plus 9 over here off to the side, and then I solve for x. I just subtracted 9 from both sides to the square root. Be careful when you take square roots, plus or minus. And so your answer was plus or minus 3i. So that gives me the factors of x minus 3i and x minus negative 3i, okay? So I put all of that together, and the answer is p of x equals x minus 1 times x minus 1 times x minus 1 times x minus 3i times x plus 3i. And then we want to clean it up a little bit because you don't really write it that way. Now notice, though, how many linear factors I have. I have 5. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 when I write them all out separately. And that's important because I have a 5th degree polynomial. So that tells me I found all of the linear factors, which is super important. So I have them all. And then before I'm completely done, I just want to clean this up a little bit. And so my final answer will be p of x equals x minus 1 cubed, as opposed to x minus 1 times x minus 1 times x minus 1 times x minus 3i times x plus 3i. That's your final answer. It's completely factored into a product of linear factors with complex coefficients. The conjugate zeros theorem tells me that if a polynomial p with a degree greater than or equal to 2 has only real coefficients, then I know that if a plus bi, that's a complex number, is a zero of p, then the complex conjugate, a minus bi, is also a zero of p. So these complex zeros come in pairs with their complex conjugates, okay, which is super helpful because that means if I give you one of them, you automatically get the second one for free, okay? So imaginary, just make yourself a note here, imaginary zeros come in pairs with their complex conjugates. Okay, super important. Okay, in our example, we're supposed to write the polynomial function of degree 4, so 4th degree polynomial. And the zeros are the square root of -9 and 1 plus 2i. We're going to write this as a product of linear factors with complex coefficients. Okay, so first off, let's write out our zeros. My zeros are the square root of -9, which that is equal to 3i. Okay, so if 3i is a 0, then that means the complex conjugate, -3i, is also a 0. Okay, and then the other one they gave me was 1 plus 2i. And so what that means is that if 1 plus 2i is a 0, then 1 minus 2i, the complex conjugate, is also a 0. So I have 4 different zeros here. I have 3i, its complex conjugate, -3i. I have 1 plus 2i, and its complex conjugate, 1 minus 2i. And so now I'm just ready to factor it. And so I've got this polynomial, we'll call it p of x. It's 4th degree, and it'll be x minus 3i, x minus -3i, x minus 1 plus 2i, and x minus 1 minus 2i. You can leave it like that if you want, or if you want to distribute the negatives and clean it up, p of x will equal x minus 3i times x plus 3i times x minus 1 minus 2i, x minus 1 plus 2i. It's 4th degree polynomial, and I have 4 separate factors. Okay, for the next part, I'm told I'm going to write the polynomial as a product of linear and irreducible quadratic factors with real coefficients. Okay, so I'm dealing with the same polynomial here, so let's just rewrite it. So p of x equals x minus 3i times x plus 3i times x minus 1 minus 2i, x minus 1 plus 2i. Okay, this time I'm going to write it as a product of linear, so 1st degree, and an irreducible quadratic with real coefficients. So real coefficients means I can't have any i's. Okay, so let's start with the first part. We dealt with this with our complex numbers. We know anytime we multiply a number by its complex conjugate, we can FOIL it out, or we can use the shortcut, a squared plus b squared. Well, a here is x. So a would be x, so that's x squared. And then the b value is either 3 or -3. It doesn't make any difference because you're going to square it anyway. So 3 squared. So this is p of x equals x squared plus 9. Okay. Now let's work on the second one. X minus 1 minus 2i, x minus 1 plus 2i. So when I'm looking for a squared plus b squared, I need to determine what a is. Well, a, sometimes it's almost easier to start with what b is because b is so obvious. B is either 2 or -2. I'll say it's -2 this time. And then everything else is a. So that means a is x minus 1. And so this will be x minus 1 squared. And so this is x minus 1 squared is x minus 1 times x minus 1. So that would be x squared minus 2x plus 1. This is actually plus 4. And then we'll put all this together. So p of x equals x squared plus 9 times, this simplifies to x squared minus 2x plus 5. So these are both irreducible quadratics with real coefficients. Okay, and I know that because if I look at the value of the discriminant, b squared minus 4ac for both of these is negative. If I want to look at the first one here, whoops. If I want to look at the first one, b squared, that would be 0 because there is no x value, so it'd be 0 minus 4 times 1 times 9, so I'd be -36. That's obviously less than 0. And then for the second one, we can work that one out. It's a little more involved. So I would have -2 squared minus 4 times 1 times 5, which would be 4 minus 20, or -16, which is, of course, less than 0. And so both of these are irreducible quadratics, again, with real coefficients. Okay, I didn't have any linear factors, but that's okay. Okay, so I'd like for you to try the next one you're on your own. Again, you're going to find a polynomial with integer coefficients, so no fractions, that satisfies the following conditions. It has a degree of 2, and then I know that 1 minus 3i is a 0. You're going to find all the zeros of the polynomial, and then you're going to write it as a product of linear factors with complex coefficients, which means all the factors are degree 1, and it's okay if you have imaginary numbers. And then for the second part, you're going to write it as a polynomial with real coefficients, so no imaginary numbers, okay? And it'll be okay if it's written, or it can be written as an irreducible quadratic. So take a shot at that and then come back and check your work. Okay, so for your zeros, you should have 1 minus 3i and 1 plus 3i, because we know that complex zeros come in pairs with their complex conjugate. Your p of x written as a product of linear factors is x minus 1 minus 3i and x minus 1 plus 3i. And then in the second part, we're supposed to write it as a polynomial with real coefficients. And so it'll be x minus 1 plus 3i, x minus 1 minus 3i. I've put the parentheses around the x minus 1 to indicate, that is the a value, because I know that when I multiply a number by its complex conjugate, it's a squared plus b squared. So a is x minus 1 squared plus b, which was 3 squared. You'll FOIL out x minus 1 times x minus 1 to get x squared minus 2x plus 1. And then, of course, 3 squared is 9. Combine all of that, and you get the polynomial as p of x is equal to x squared minus 2x plus 10, which is an irreducible quadratic. And I know it's an irreducible quadratic because the discriminant, b squared minus 4ac, is less than 0. In fact, the value of the discriminant is -36, and so that obviously is less than 0. For this problem, we're told that p has degree 4 and zeros at -1 and 3 plus 2i, and then we're asked to determine the zeros of p. So again, we know that when we have a complex zero, such as 3 plus 2i, then its complex conjugate is also a zero. So in this case, 3 minus 2i. And then we're told we have a zero at -1. So the zeros are 3 plus 2i, 3 minus 2i, and -1. Now, I'm told this is a degree 4 polynomial, so that's going to come to play in just a second. So if I know that 3 plus 2i is a 0 and 3 minus 2i is a 0, remember if it's degree 4, then I have to have 4 separate factors. And so one of these must be to the second degree. Well, it has to be that the 0 at -1 is the second degree, because if it was 3 plus 2i, say, that was to the second degree, then remember they come in pairs. That means 3 minus 2i would have to also be to the second degree. And at that point, I've got too many factors. So it can't be 3 plus 2i. It has to be that -1 is the one that's going to be to the second degree. And then we're supposed to write this as a product of linear factors, so everything first degree, with complex coefficients, which means that your coefficients may be imaginary. They don't have to be, but they can be. So anytime you're required to have all linear factors, you have to include the option that they can be imaginary. So p of x equals, I'll write the real one first. So x plus 1, because if the 0 is at -1, then the factor is x plus 1. We already said this one is the one that has to be to the second degree. The second is x minus 3 plus 2i, and then finally x minus 3 minus 2i. Okay, so if I were to list these out individually, I'd have 4 separate factors. I'd have x plus 1 times x plus 1, x minus 3 plus 2i, x minus 3 minus 2i, and so a fourth degree polynomial. And of course, I have a fourth degree polynomial here because this is 2. These are both to the first degree. So if I add up all the degrees, they total 4. For the next part, I'm told I'm going to write the p of x as a product of linear and irreducible quadratic factors, but this time I'm limited to real coefficients, so I can't have any imaginary numbers. So the first thing I'm going to do is I'm going to rewrite the problem that I had above, p of x equals x plus 1 squared. And then when I rewrite my factors that have my complex coefficients, I'm going to group them a little bit differently. I'm going to distribute the negative sign through for each of these. Be careful when you do that. And so I'll end up with x minus 3 minus 2i times x minus 3 plus 2i. So I've got two complex numbers, and I know when I multiply a complex number by its complex conjugate, I can shortcut that, and that's a squared plus b squared. So I need to identify what's a and what's b here. Well, a will be x minus 3. And then b is either positive 2 or negative 2, and it doesn't make any difference because when you square it, it's going to be positive anyway. But it's important to put the parentheses around the x minus 3. I always think it's easier to identify b first because b is the value that comes in front of I, and then just know that everything else is the value for a. So, okay, so I've got p of x equals x plus 1 squared, and so a squared will be x minus 3 squared. It's going to multiply all of this, plus b squared, and then b is either 2 or negative 2. You can decide. It doesn't make any difference. I just wrote negative 2 because it's the first one I had listed. And then I'm going to continue to simplify this. X plus 1 squared just gets dragged along. X minus 3 squared is x squared minus 6x plus 9. And then negative 2 squared, of course, is plus 4. P of x equals x plus 1 squared times x squared. We're going to simplify, minus 6x. 9 plus 4 is 13. Okay. And that's it. So this is now written as a product of linear factors. Now, I'm going to point something out to you here. X plus 1 squared is still a linear factor. Don't get confused, okay? It's a linear factor because you could write it as x plus 1 times x plus 1. So those are still linear factors, two of them. We've just simplified by making it x plus 1 squared. And then the irreducible quadratic here The irreducible quadratic is x squared minus 6x plus 13. And again, I can do a quick check to make sure it really is an irreducible quadratic, that it can't, what that means, remember, is it can't be factored without using imaginary numbers. Well, this came from, remember where this came from. The factors are here, x minus 3 minus 2i and x minus 3 plus 2i. So we know what the factors are, and they obviously have imaginary numbers, so we know this is an irreducible quadratic. All right, so for the next problem, I'd like for you to try this one on your own. We find a polynomial p with real integer coefficients, so integers counting numbers, okay, that satisfy the given conditions. We're told that it has degree 4, and it has zeros at 2 and 2i. So first you're going to write it as a product of linear factors with complex coefficients. So that means that if you have imaginary numbers, that's okay. And then you'll write it as a product of linear and irreducible quadratics, this time with real coefficients, so no imaginary numbers. So work on that, come back and check your work and see how you did. Okay, so for the first part, you should have noticed that the zeros are 2, 2i, those were given, and then negative 2i will also be a 0 because, again, they come, complex zeros come in pairs with their complex conjugate. We write p of x as a product of linear factors. You should have that p of x equals x minus 2 squared times x minus 2i times x plus 2i. Make sure that you have x minus 2 squared because we know this is a 4th degree polynomial, and so that gives you a 4th degree polynomial. Again, the complex coefficients, or the factors with the complex zeros, come in pairs. So each of those, if you were to make one of those the one that was squared, 2 of them, then the other one would also have to have 2. And then when you had x minus 2 as well, you'd have a 5th degree polynomial, so it'd be too much. So through process of elimination, you can tell it's x minus 2 that has to be squared. Part B, you're supposed to write it as a product of linear and irreducible quadratic factors with real coefficients. You should have p of x equals x minus 2 squared times x squared plus 4. And the x squared plus 4, of course, comes from foiling, or you can use the shortcut a squared plus b squared for x minus 2i times x plus 2i. Okay, so moving down below, we've got sort of just a summary here to pull it all together. So these are the characteristics of zeros for a polynomial function, okay? This is sort of what we've learned. So we're going to pull this all together in one place. So if some number a is a 0 of the polynomial, then we know that x minus a has to be a factor, okay? The factor theorem tells me that. If a is a 0 of multiplicity m of some polynomial, then x minus a raised to that same multiplicity of m must be a factor when we factor it completely. A polynomial p that has a degree greater than or equal to 1 has at most n distinct zeros. Okay, so what that means is if I have, let's say, a polynomial p of x, and let's say it's to the 4th degree, and I just wrote 5. Okay, let's say it's to the 5th degree. So it's a 5th degree polynomial. Then that means it has at most 5 distinct zeros. Okay, now distinct being, not like the others. So maybe one of them is x equals 0, x equals negative 2, x equals 3, I don't know, x equals 1/2, and x equals 7. Let's say those are the zeros. These are distinct. They're all different than the others. Now, if I were to take one of these and it was to occur more than once, so it had a multiplicity, let's say 3 had a multiplicity of 2. Okay, well then in that case, when you count the multiplicity, then your number of zeros still has to total 5. So that means I couldn't have all of these. Maybe I got rid of x equals 7. Okay, if the rest of these were all multiplicity 1. So back to the definition, a polynomial has of degree n greater than 1 has at least n distinct zeros, not like the others. P has exactly n zeros. If a 0 of multiplicity m is counted m times. Okay, so again, here's another example. P of x equals x minus 2 cubed times x plus 1 squared. Now this has 2 different zeros. The zeros are at 2 and at negative 1. Okay, now we're told we know this is a 5th degree polynomial. It can have at most 5 distinct zeros. This one only has 2. Okay, So the fifth degree polynomial. Well, it still has that number of zeros. It has 5 zeros as long as we count the 0 at 2 3 times, and we count the 0 at -1 2 times based on their multiplicities. 4 says that if the polynomial p has only real coefficients and if a plus bi is a 0 of p, then we know that a minus bi is also a 0 of p because, again, they come in pairs with their complex conjugates. Okay, for the next example, we're told we're going to write the polynomial p of x that has the following characteristics. So it's going to be degree 8. So what that means is that the sum, that symbol means sum of the multiplicities has to equal 8. Okay, it's going to have real coefficients. So the polynomial itself has real coefficients, no complex numbers. So that means the polynomial, when we factor it, it's going to be a product of linear and irreducible quadratics. Okay. Our zeros are at -2, 3, and 3 plus 2i. So again, we're going to have another 0 at 3 minus 2i because they come in pairs. And then the real zeros, we're told, have a multiplicity of 3. So the real zeros are at -2 and 3. So that means if my 0 is -2, my factor is x plus 2, and that's going to have a multiplicity of 3. And then if my 0 is 3, my factor is x minus 3. Again, that will have a multiplicity of 3. And then finally, the leading coefficient is 5. Okay, so we put all of this together to come up with our polynomial. So p of x is going to equal, my leading coefficient was 5, times, my first 0 is at -2, so the factor is x plus 2, and I know the degree is 3. My second 0 is at 3, so the factor is x minus 3. Again, the multiplicity is 3 because I was told that the real zeros have a multiplicity of 3. And then 3 plus 2i is my next 0, so I'll write that as x minus 3 plus 2i. And then finally, x minus 3 minus 2i. Okay. Now, I'm not done because I'm told that it has to have real coefficients. Well, right now I have imaginary numbers. So what I'm going to have to do, I've got to convert this into a product of linear and irreducible quadratics. So I'm going to have to simplify this and make it into an irreducible quadratic. So p of x equals 5 times x plus 2 cubed times x minus 3 cubed. And then this, of course, will be a squared plus b squared. So let's do this. I'm going to give it one more step. I'm going to rewrite this, distribute the negative through. So this will be x minus 3 minus 2i, distribute the negative, x minus 3 plus 2i. Then we'll do our shortcut with a squared plus b squared. Okay, a is x minus 3. So this is x minus 3 squared. B is either 2 or -2. And we'll simplify. P of x equals 5 times x plus 2 cubed, x minus 3 cubed. X minus 3 squared is x squared minus 6x plus 9. -2 squared, of course, is +4. We're almost there. 5 times x plus 2 cubed times x minus 3 cubed times x squared minus 6x plus 13. And then make sure you double check. When you're done, you should have degree 8. And so this x plus 2 is a linear factor to degree 3. X minus 3 is a linear factor, degree 3. So add those. 3 plus 3 is 6. And then this irreducible quadratic is degree 2. So when you sum up the degrees, they equal 8, which is what I needed. Okay, and so this is now written as a product of linear and irreducible quadratics with real coefficients. So I realize this can be a little cumbersome, but you really need to understand what it is you're finding. Okay. All right, so for the next portion, you're going to write a polynomial p of x with the following characteristics. This time it's degree 9. Real coefficients again. The zeros are at 0, -4, and 5i. We're told the 0 at 0 has a multiplicity of 4, the 0 at -4 has a multiplicity of 3, and the leading coefficient is 2. So I want you to pause here, write this, come back and check your work. Okay, so your answer should be p of x equals 2x to the 4th times x plus 3 cubed times x squared plus 25. Again, we know that this is supposed to be degree 9. So 4 plus 3 is 7 plus 2 is 9. So that's your final answer. Okay, so for this problem, we are going to determine all real and complex zeros, and then we're going to write the polynomial as a product of linear factors with complex coefficients. So again, if complex coefficients means you can have imaginary numbers if you need to, but all the factors have to be to the first degree. Okay, we're going to identify all the zeros of the polynomial, and then we'll determine if those zeros are real or non-real complex. Okay, so for our first problem, we're given q of x equals x to the 4th plus 2x squared minus 8. So 4th degree, and we've got to figure out how to factor this. So this is sort of a special case for factoring. Now, normally when we factor, we either look and see is there some in each of the terms, is there some value I can factor out of each term? So out of the first two terms, I could factor an x squared, but there's no x's in the last term, so that doesn't work. I could factor a 2 out of the second two terms, but there's no 2 in the first term, so that doesn't work. So what I've actually got here is a special case of a quadratic. So if I rewrote this as x squared, that's the same as x to the 4th, plus 2 times x squared minus 8. You can kind of start to see a pattern that this is actually a quadratic, okay? So what I like to do is do a substitution here to make it even that much more obvious. So let's just say, let a equal x squared. Okay, we're just going to arbitrarily assign this variable a, and we'll say a is going to be the same as x squared, and we're going to do a substitution here. So if that's the case, then instead of x squared, I'm going to have a. So this is a squared plus 2 times a minus 8. So now my problem is a squared plus 2a minus 8. Now that you should definitely recognize that's a quadratic. That can be factored, and factored really pretty easily. So this factors to a plus 4 times a minus 2. Now that we've got our factors, we need to go back because we know it's not really a that's in the problem, it's x squared. So we're going to go back and we're going to sort of, I guess we'll undo our substitution. And so what that means is that x squared plus 4 times x squared minus 2 are the factors of the original problem, x to the 4th plus 2x squared minus 8. I just used that a substitution just to make my life a little easier, to make things a little more obvious, okay? And so now that I've got my factors, I've got two factors that are, well, one of them is an irreducible quadratic and the other one is not. But I'm supposed to factor this into a product of linear factors. Okay, so I can't leave it like this because as it is right now, I have two quadratic factors. So off to the side, let's find the factors for each of these. So x squared plus 4, we can just set this equal to 0 and solve. I'll subtract 4 from both sides. X squared equals -4. Take the square root of both sides, and so x, be careful here, this is plus or minus, don't lose that along the way. X equals plus or minus the square root of -4, which is plus or minus 2i. Okay, so that's my first one. Let's do the second one. X squared minus 2 equals 0. Add 2 to both sides. And so x squared equals 2. Again, I'll take the square root of both sides, plus or minus. And so x equals plus or minus the square root of 2. Those are my zeros. Okay, so using my zeros, I can now write this in factored form. So q of x equals x squared plus 4 factors to x minus 2i and x minus negative 2i. Okay, x squared minus 2 factors to x minus the square root of 2 and x minus negative the square root of 2. And then I want to clean this up a little bit. And so q of x equals x minus 2i. I'm just going to distribute my negative times x plus 2i. Plus it helps to see now that these are complex conjugates. X minus the square root of 2 times x plus the square root of 2. And so now this is factored, fully factored as a product of linear factors. Everything is first degree with complex coefficients. So, and then the next part of the problem said to identify all the zeros. I found my zeros here. And then we're supposed to determine if they are real or non-real complex numbers. Well, x equals plus or minus 2i, that's non-real complex. Okay, because it's imaginary. So those are non-real complex. And then x equals plus or minus the square root of 2. Square root of 2, we may not love working with that number, but it's a real number. So these are real. Okay, and so now that's your final answer. So for the next one, p of x equals x cubed minus 3x squared plus 25x minus 75. So I've got 4 terms. Anytime you have 4 terms, you want to try to factor by grouping. And so you figure out what can I factor out of the first 2 terms, and then what can I factor out of the second 2 terms. So for the first 2 terms, x cubed minus 3x squared, I can factor out an x squared. That'll leave me with x minus 3. And then the second 2 terms, I can factor out a 25. That leaves me with x minus 3. Now, because these match, then I know I can factor by grouping. Okay, if these didn't match, these factors didn't match, then this doesn't work. Don't fall into the trap of thinking that everything can be factored by grouping. That's not the case. These match, and so these each have a common factor of x minus 3, which can be factored out. And that leaves me with x squared plus 25. Now, again, I'm supposed to have a product of linear factors, and x squared plus 25 is not linear. So x squared plus 25, I've got to factor that, set it equal to 0. So x squared equals negative 25. Take the square root of both sides. And if you wanted to use the quadratic here, you could. It just takes a few more steps. So this is plus or minus 5i. Okay, so I need to factor this, finish factoring. So p of x equals x minus 3 times x minus 5i times x plus 5i. Now it's fully factored into a product of linear factors with complex coefficients. For the next part, we were supposed to identify all of our zeros. So my zeros were 3, 5i, and negative 5i. Okay, and then we identify if they're non-real complex or they're real. Well, 3 is real, and 5i and negative 5i are non-real complex or imaginary. You can call it either. It doesn't really make any difference to me. Non-real complex I know can feel a little cumbersome. Imaginary is fine. Okay, for number 3, I want you to try that one on your own. X cubed plus 4x squared plus 4x plus 16. Again, you're going to fully factor it into a product of linear factors, identify the roots, and then determine if the roots are non-real complex or real. Come back and check your work. Okay, so your final answer should be that L of x equals x plus 4 times x minus 2i times x plus 2i. Again, product of linear factors, everything's first degree. Your roots are x equals negative 4, positive 2i, and negative 2i. Negative 4 obviously is a real number. 2i and negative 2i are non-real complex.